In the last couple of videos, we've looked at antiderivatives, that is, undoing differentiation, and we've also looked at areas of functions under curves. What on earth have these things got to do with each other? Well, it turns out these are intrinsically related, and they're intrinsically related through the fundamental theorem of calculus, which was a major stepping stone in the development of calculus. Let's have a look at that just now. Consider the following picture. The shaded area between a and x is the area of this function y equals f of x. The shaded region is the area from a to x. So we can set this up as an integral. It's the integral from a to x of the function, and instead of x, I'm going to use t as the variable. So remember, the variable in the integrand is just a dummy variable. It doesn't matter what symbol we use for it, provided there are limits on the integral. Now this integral I've written down is actually a function of x. So let me write this as g of x. And so the area from a to x is equal to g of x, provided f is positive. Now let's ask the question, what is the derivative of g with respect to x? Let's have a go at calculating this from the definition. Now, the numerator of this is the complicated bit, so let's just write out what that is. Okay, so in terms of these two integrals, there's a difference between these two integrals. Let's interpret that geometrically. So if I consider x and x plus h, where h is some finite number, then the difference between these two integrals is actually the difference in this area here. So this equals the area of the shaded region. And this is approximately equal to, on the left-hand side, the function height is f of x, and the width of it is h. This is approximately equal to h times f of x, with some small error owing to the change in the function value in this region. Now, as we're going to take the limit as h tends to 0, that small change will get less and less relevant. So therefore, we can write that g prime, the limit as h tends to 0 of h times f of x over h. And of course, this is just f of x. So that's a really remarkable result, and this is known as the fundamental theorem of calculus, part 1. It's the first part of what forms the fundamental theorem of calculus. Let's just recap this. What we've shown is the derivative of an integral where the upper limit is x of f of t dt is equal to f of x. The derivative of an integral is the function itself. Now let's think about what else we've learned. G prime equals f of x, so that means that g is an antiderivative of f. And if I let the function capital F equal g of x plus c, that means capital F is also an antiderivative of f, and in fact is the family of all antiderivatives of f. G is a particular antiderivative which satisfies the following. It's the antiderivative such that g of the number a is the integral from a to a of f of t dt, and geometrically this means that this is no area at all. We're not integrating over any range of the function. And so this is just equal to 0. And that implies then that f of a is just equal to this constant c in my set of all antiderivatives. And hence, this means that f of b, the upper limit of integration, is equal to g of b plus c, or, let me write this out in a different way, f of b minus f of a is the integral from a to b of f of t dt. So what we've done there is show how to evaluate an integral given an antiderivative of the function. If we know an antiderivative of the function, doesn't matter which one it is, we can evaluate the integral by just calculating the difference in the function between the two limits. And this is the second part of the fundamental theorem of calculus, and it's known as the evaluation theorem. The two parts of the fundamental theorem of calculus then are that if I differentiate an integral, I recover the integrand, and to evaluate an integral, I need to know an antiderivative of the function, and then the integral between two limits a and b is the difference in the antiderivatives at a and b. Let's reconsider the example of the integral from 0 to 2 of x cubed. Now, we evaluated this using the summation technique, what's called a Riemann sum. Let's now try this using antiderivatives. Now, an antiderivative of x cubed is just x to the 4 over 4, since if I differentiate x to the 4, it's 4x cubed. Therefore, using the evaluation theorem, the integral from 0 to 2 of x cubed dx is x to the 4 over 4 evaluated at 2 minus x to the 4 over 4 evaluated at x equals 0. And I'm using a vertical line with a number to denote where I evaluate that part next to it. So this is just equal to 2 to the 4 over 4, which is 4, as we saw earlier. So the key thing we've learned is that derivatives and integrals are inverse processes, in the sense that d by dx, the integral up to x, and the integral, so the integral from a to b of f prime t dt is the difference in the function between the two limits. Often we won't have limits to the integration, and this is called an indefinite integral. And this is a shorthand for the set of antiderivatives of little f, because, and note this is a family of functions. Now, the basic indefinite intervals are usually tabulated, and we can find them from just looking at tables of derivatives as just the inverse process of differentiation. Examples include the integral of x to the n dx is x to the n plus 1 over n plus 1, because if I differentiate x to the n plus 1, I get a factor of n plus 1, which leaves me with just x to the n. And note that because it's an indefinite integral, it represents the family of antiderivatives to x to the n, I must add on an arbitrary constant here. In the case of n equals 1, the integral of 1 over x dx, and I know this is log x because if I differentiate log x plus a constant, I get 1 over x. And this, of course, is for x greater than 0. Similarly, the integral of sine x is equal to minus cosine of x, because if I differentiate cosine, I get minus sine. You should go through a table of integrals and understand where they come from.